This video will give you an introduction to course details, like a few things that you'll find in the syllabus, and also talk about the foundational material that we'll be using this semester. Things like how do we describe sizes and time, how do we use units. You'll have your assignments due this week on mastering physics, as well as reading, of course, in our text that you can follow along with, and you'll be introduced to learning catalytics and do problems in class on Monday. Often I start classes with a picture that I call, "What is this?" Gives you an opportunity to get yourself logged into learning catalytics and to consider something that is relevant in our physical world, where we see physics in action. In this case, you might think that this was a glass structure. In fact, this is a snowflake. And the next slide, after you guess, the next slide describes some feature of that item that is relevant to the discussion of the day. This snowflake is actually a single crystal. Well, no, this is actually an aggregate of ice crystals that have come through the Earth's atmosphere and were photographed. We'll be talking about symmetry today, and snowflakes exhibit significant symmetry, and that's one thing that makes them so appealing to us. A single crystal can actually exhibit up to six-fold symmetry, which means six different rotational positions at which it will be symmetric. Most snowflakes, however, are not completely symmetric. So our various "what is this" pictures will again give you an example of something that's relevant to the course and that day's discussion that exists in our world. So this week is a little bit unusual. I'll be presenting at an optics conference on the other side of the country, and so I will not be able to be in class. Instead, you will go to class on Monday and Wednesday, and these sessions do count towards your overall attendance. You will not go to class on Thursday. On Monday, you'll watch either before or after the video, this video, in fact, and then during class, you'll work on worksheet problems. On Wednesday, you'll do a pre-class assessment in the class period. So go to class on Wednesday, you'll do a short multiple choice assessment, and then you'll leave. Again, don't come to class on Thursday. Right, so I'm going to talk a little bit about what physics is and some of the things that differentiate physics from our other disciplines. So in physics, what I want you to do is to start really believing what you see. So if you see something like gravity, you see it because things fall down. This cat, for example, does fall down, and it does it very gracefully. And in fact, cats exhibit some really interesting physical mechanics by maneuvering their body and landing safely on their feet. If you want to see an example of that, you can go to this video link of cats landing on their feet. However, while we want to believe what it is that we see, it's also really important in physics to simplify everything, basically, into something that can be described with the tools that we have. So this is one of my favorite cartoons. It's a standard joke, actually, that this is a field of physics, cows. And what's unique about these cows is they show absolutely nothing that is cow-like except their spots. So these cows have been simplified to spheres, and the joke is that we talk about spherical cows. A spherical cow really does not give you any information about the cow except where it is. So this is the idea of simplification. We start with something that's very concrete, like a photograph of a cow, and then we could simplify it by taking away all the color. We could simplify it more by taking away the features of it and just representing its extent and its location as a rectangle. And then we could simplify it more by showing its position as its center of mass. So that's what we do most of the semester. We simplify everything to its position. The object is located at its position, and we don't consider the extent of it or its shape. And a little more simplification. This is biology to a physicist. So physics, we'll see some pretty interesting things and pretty remarkable feats. But it's important to remember that there really is no magic in physics. And that's actually magical to me, that everything that we do and everything that we see can be explained. That's really awesome. That's why I love physics, because I can look at things and look for how I can explain what's happening. Now, how will you learn physics? First thing that you should do is read the syllabus, which is available on Blackboard. And by that, I actually mean read the syllabus. You'll complete the syllabus quiz, which is on learning catalytics. So after you get yourself set up with learning catalytics, you'll find the syllabus quiz available there and complete it. Next week, we'll talk about any additional questions that you have, and I can clarify any details that you have about the course structure, etc. You will be expected to actually do some work before class each day and each week. On each week, there's a pre-lecture assignment, and that is an assignment on mastering physics about the concepts of that week. It's very general, very conceptual, and the expectation is that you will have looked at the appropriate sections in the textbook. That means your first reading of those textbook sections. You'll also try the suggested worked problems. This is tough, and it's something that will make the class make much more sense to you. There's a lot that we have to do here, and learning physics is actually pretty hard. I want you to know where you should be every day, and so I make it very easy for you by posting on Blackboard and the assignments and readings for that day. So you refer back to Blackboard each time you have any questions about assignments that are due. I want to make a note that as you looked at the syllabus, you noticed course breakdowns and percentages, grading breakdowns. In this course, it's actually necessary for you to do everything in the course in order to get a good grade, and that's not just the exams. The exams are a very significant part, but they are not the only part of the grade. So please pay attention to all of the aspects of the course that are involved in your grade. And most of your homework will be submitted online through Mastering Physics. We'll be talking about this a lot. There's resources on Blackboard already, and you received emails from me and will receive more. Please ask any questions of me or ask the help at Pearson for Mastering Physics questions. Our in-class questions will be submitted with Learning Catalytics, which is actually linked to Mastering Physics. So a little more on homework. We'll have homework sessions every Thursday, and those will start not this week, but next week. Location will be announced. Please note that in order to do the best with the homework, you should be writing out all the problems on your own paper. The assignments are on the computer, and it's very tempting to just look at the problems on the computer and not write them down. However, you will find that you don't know how to recreate what you just did. And that's what's necessary in order to do well on the exams and actually to learn how to use the tools that we're learning through the semester. So, to go over what you should bring to class, bring your notebook or some kind of paper to take notes with, your textbook for reference for specific problems and for help as you go through the work, and something to write with. Bring a calculator, and of course bring whatever you need to keep yourself going during the day. In addition, you have to bring your cell phone, a tablet, a computer, some internet-enabled device. You can refer back to this, think about how to keep yourself organized, and look at my suggestions, including how to record your class notes, reading notes, homework solutions, and exams. Keep all of those aspects, and this will help you when you're going through the things that we've done in class. All right, so today we're going to talk, that was already the introduction, we're going to talk about the scientific method, physical quantities and units. Then we'll look at symmetry and time and length scales, and then finish by doing some conversions between different length scales. So the scientific method is what we call an iterative process by which we try to figure out the laws of nature. Iterative processes are ones that you repeat. So this process, we make an observation, for example, and then we induce a hypothesis. We then make a new prediction, test our prediction, make another observation, etc. You could start this iterative process at any of those three steps. Start with a prediction, or start with a hypothesis, or start with an observation. You'll be testing this in lab in a fairly formulaic way, but you are still doing this scientific process. Each time you find an error, you'll change what you're doing. And this then is how we develop laws, the laws of physics, by predicting, observing, and confirming our hypotheses. So one more bit on the course details. I'm going to show you an example of this, but we actually do want you to take out your cell phone in class, or your tablet, computer, etc. If you don't have something that you think will work, please talk to me or email, and most likely the solution will be to borrow somebody else's internet-enabled device. It can be anything with the internet. So you'll go to Mastering Physics, and from there you can link to Learning Catalytics, or you can go directly to Learning Catalytics and register with your Mastering Physics username and password. Okay, so this would be an example. This is what the Learning Catalytics questions will look like. LC stands for Learning Catalytics. And this question says, I have 2 coins in my pocket, together worth 30 cents. If one of them is not a nickel, what coins are they? And we think about this. This is one of your worksheet questions, so I'm not going to tell you the answer right off, but we think about this, and it is very easy to read it as neither of them being nickels, rather than only one of them not being a nickel. So we make an assumption based on how we've read the problem, and that assumption can actually lead us towards not being able to find a solution. After you answer the Learning Catalytic questions, in class, we go through the answer and discuss the question. Right, so when we're dealing with physical quantities, we use what's called the International System of Units, abbreviated SI, which define all of our standard units. And for example, the unit of length is defined as a meter and is abbreviated M. The meter has been defined in different ways throughout history. The current definition is quite high tech, let's say. It's defined as the length of the path that light takes during a certain time interval, which is related to the number of vibrations of a cesium atom. There's a really cool resource at NIST, the National Institute for Standards and Technology, that'll tell you a bit more about things like the origin of the units. This is a meter. This is an early picture of the meter. So we're going to use prefixes, and if you're unfamiliar with prefixes, take a little time to look through these, practice saying the different words. The ones that we focus on are the ones that you're probably more familiar with, like the prefix for 1,000 or 10 to the third, which is kilo. In other words, a kilometer is 1,000 meters. And then the prefixes for milli, like millimeters, micro, micrometers, or microns, nano, etc. And we could put millimeter or millisecond after that prefix. Also nanosecond or nanometer after the nano prefix. And that tells us the order of magnitude of the unit that we're talking about. So again, go through those, see what you can, see which ones are familiar and which ones you'd like to just learn about or are kind of cool to see. One that I particularly like is the femtosecond. The femto stands for 10 to the minus 15. And the reason I like it is because lasers, this particular picture on the right is actually a picture of a femtosecond laser, well, the guts of the femtosecond laser. And that means that in a femtosecond laser, light actually appears only for a 10 to the minus 15 seconds, more like 50 femtoseconds or 100 femtoseconds. The light is pulsed in very, very, very short times. That's incredibly short. So we never hear about femto because in most of our lives, because very few things happen on that kind of time scale. But I will tell you more about femtoseconds another time. Right, so moving on to symmetry. The idea of symmetry is that any object exhibits symmetry when a certain operation doesn't change how it looks. So if we have a triangle, what can we do with that triangle in the top left? We can rotate it. How many degrees do we have to rotate it so it looks exactly the same? The picture on the right shows us that if we rotate it 120 degrees, it looks the same. This is an equilateral triangle, of course. Those are rotation, so this means it has a rotational symmetry of 120 degree rotation. There's also reflection symmetries, and in this case, can we reflect the object across any axis and have it look the same? And the answer is yes. If we draw an axis from the corner, from one corner of the triangle to the center of the opposite side, we will get the identical triangle on each side. So we'll get reflection symmetry. Seems pretty straightforward. And symmetry is really useful for simplifying problems in particular, and also just recognizing the patterns around us. Seems pretty straightforward, but one of the questions that you'll be working on Monday in class is this question: what symmetries do you observe in this pattern? And it's a little challenging. If we look at B, for example, does it have rotational symmetry or reflection symmetry? And it has one or the other, but it actually doesn't have both. So think about which symmetries each of these things observe. Again, you'll come back to this in class. All right, so lengths. It's an interesting older definition of the meter. The meter in 1791 was defined as 1/10 millionth of the length of a quadrant along the Earth's meridian. In other words, it's a quarter of the way from the equator. It's a quarter of the way all the way around the Earth. So the quadrant goes from the equator to the North Pole. And that was defined as a certain number of meters. Then a meter was 1/10 millionth of that. Seems like an awfully awkward definition, but we had to come up with something, some standard unit that everybody could identify with. And you are going to use that definition of the meter in one of your worksheet problems also. So a quick look at sizes. Sizes here are grouped into different clusters. Very, very small things referred to as subatomic particles, and those are on the order of 10 to the minus 16 to like 10 to the minus 10 meters. Then we have things that are made of clusters of atoms, like viruses and cells. Then we move into the human scale, like a human, and then a very large animal, like the blue whale. And as we get into even bigger clusters, we have clusters of matter, like the Earth, and then we have clusters of stars, and these orders of magnitude get huge. Star clusters on the order of 10 to the 22 meters, and the observable universe on the order of 10 to the 28 meters. You hear me say on the order of for each of these numbers, and we'll come back to the order of magnitude soon. Right here. So orders of magnitude. We're dealing with huge ranges of sizes and huge ranges of time often, but in this case, huge ranges of sizes. And so we want to be able to round values to the nearest power of 10. These are orders of magnitude. The way we round on orders of magnitude is different from the rounding that you've probably learned already. And this goes that any number between 0.3 and 3 would be defined as an order of magnitude of 1, and any number greater than 3 but less than 10 times 3, in other words, less than 30, has an order of magnitude of 10. Okay, so if we have 180 seconds, for example, we write that in scientific notation as 1.8 times 10 to the 2. And 1.8 is an order of magnitude of 1, so the total order of magnitude of the number is 10 to the 2. Now, Earth's circumference, we write in scientific notation as 4 times 10 to the 7 meters. And here, 4 we round to an order of magnitude of 10. So the total order of magnitude of the number is now 10 to the 8 meters. We've got an example of this also in your worksheet. Once we've defined length, we can think about defining time. And the standard unit of time is defined as the number of vibrations of a cesium atom, or is defined as the length of time it takes for a cesium atom to vibrate a huge number of times. That atom is vibrating very, very fast. There are pretty amusing previous definitions of the second. You can go back and look at those if you're interested in seeing how time has been defined over time. And time intervals, we've talked about prefixes already, but time intervals we can think about from very, very short to very, very long. And think about the difference between the period of a human heartbeat and the length of a human lifetime in terms of seconds, and then the age of the universe. Huge orders of magnitude difference. Time is pretty fascinating because it only goes in one direction. So we can actually define before. We always know what before means, and after, or first and second. Those things don't work with distance or length unless we give ourselves some reference points, but time always goes forward. And that's kind of bad when we realize that time can't run backwards. So for example, if you break an egg, you can't put it back together again. We can't turn that time backwards, and that's an example of entropy. Now, the last thing we want to talk about today is units and conversions. We've been looking at scales. But units are really, really important, and a sense of scale is important. When you look at this picture, can you tell which one is taller? You probably can, but you might not realize just how much taller the one on the left is than the one on the right. I'll give you an example of that in our next class. So it's important for us to be able to talk about units, or to describe any length or time in terms of a standard system of units. So we use these SI units, or Système International units. The SI units are meters, kilograms, seconds. Those are the three that we will be dealing with. We will not, in this class, work with the ampere or really work with temperature much, or the mole, or the candela. So meters, kilograms, and seconds are SI units. It's really important to be able to go back and forth between one set of units and other units because we live in a world, for example, where we talk in inches, but everything we do in physics is in meters. So you want to get a sense of how inches relate to meters, for example. So here's the way to do it. We write ratios. Ratios are the physicist's friend. In this case, a ratio, what we can do is make a ratio equal to 1 as a conversion factor. So 1 inch is the same thing as 25.4 millimeters. In other words, 1 inch divided by 25.4 millimeters equals 1. But also, 25.4 millimeters divided by 1 inch equals 1. So we can use that. We can multiply any number by 1 without changing it, which means we can multiply any number by those conversion factors without changing them. So we can use them for unit conversions. We use these ratios of 1 for unit conversions. For example, if we want to convert 4.5 inches into millimeters, we start by writing 4.5 inches, and then we multiply 4.5 inches by a ratio of millimeters per inch. And you notice that when we write it that way, we can see that the inches cancel, as any numeric fraction would. And so we're left with multiplying 4.5 by 25.4 millimeters, and we get 1.1 times 10 to the 2 millimeters. Here's a longer example. So express 1.08243 times 10 to the 19 nanometers per year in meters per second. We're going to break that down into two conversions. First, we're going to express the number of seconds in 1 year. In other words, we're going to find seconds per year. So if we want to find seconds per year, we start with seconds per minute multiplied by minutes per hour, multiplied by hours per day, multiplied by days per year. Notice that all of these minutes cancels with minutes, hours cancels with hours, day cancels with days, and we're left with seconds per year. Write this down on your own paper to keep up with the slide. When we multiply all that out, we get 315,36000 seconds per year, or in scientific notation, 3.1536000 times 10 to the 7 seconds per year. Now we can actually do our question. 1.08243 times 10 to the 19 nanometers per year equals 1.08243 times 10 to the 19 nanometers per year times the conversion between meters and nanometers. So you would have to look back at your prefixes to remember what a nanometer is. So we're at 10 to the minus 9 meters per nanometer. And then multiply by years per second. So we just found the seconds per year. I can flip that and write it, instead of seconds per year, I can write years per second. And when I look at my original units, the nanometers on top cancel with the nanometers on bottom, so I'm left with meters. The year on the bottom cancels with year on top, so I'm left with seconds on the bottom. And I get 3.43236 times 10 to the 2 meters per second. And you may wonder how many significant figures to keep here. We'll talk about significant figures in the next class period and practice more with significant figures. To remind you where you can find me, I'm located in the South Classroom building when I'm in town, and my office and lab are both over there. We do not have finalized office hours yet, but there will be office hours at some time on Tuesday, and also Thursday evening homework session primarily for our class, and Friday office hours at some point because we have homework due on Friday. And also by appointment. You can always email me and see if we can find a convenient time for both of us.